In the previous lesson, we learned how to implement a simple low-pass filter. In this lesson, we will learn the process of designing more advanced filters built with op-amps. We will start by learning what are the different kinds of filters that we can create. In these plots, you can see the frequency response of different filters. We already know the low pass, shown in the top left. We can observe that after a frequency of 1 radian per second, the magnitude of the signal starts decreasing. The low pass filter removes high frequencies. On the top right, we can see the high pass. Its behavior is complementary to the low pass filter. This specific filter attenuates any frequency lower than 1 radian per second. On the bottom left, we have a bandpass filter. This kind of filter leaves a range of frequencies unaffected and attenuates the low and high frequencies. The bandpass can be built by a combination of a low pass and a high pass filter. On the bottom right, we have the band stop filter, also known as notch filter. This filter attenuates a range of frequencies, leaving the high and the low frequencies unaffected. It can also be built with a low pass and a high pass filter. By making different combinations of the basic filters, we can create all kinds of strange frequency responses. For that reason, we will focus on designing low pass and high pass filters only. Two low pass filters can have different characteristics. There are different parameters that make them different. One of those parameters is the slope. The slope defines how steep the frequency response is. For example, in the bottom plot, we can see that comparing the attenuation at 1 radian per second against the 10 radians, there is a difference of about minus 40 dBs. This filter has a slope of minus 40 dB per decade. A decade is jumping from a reference frequency to a frequency that is 10 times larger. We measure at 1 radian per second, then we measure at 10. The slope can also be given in octaves. An octave is equivalent to multiplying the reference frequency by 2. For example, the change from 1 radian per second to 2 radian per second is around minus 12 dBs. Octaves are more commonly used in musical applications. There is a relation between the order of the filter and the slope. The basic RC filter we explored in the previous lesson has a slope of minus 20 dB per decade or minus 6 dB per octave. This is a first order filter because it has only one capacitor. The one in this example is a second order filter, and that's why it has a slope of minus 40 dB per decade. In general, as the order of the filter increases, we can expect a steeper slope. The other important parameter is the cutoff frequency. We have mentioned this parameter before. It defines the frequency at which the filter has a significant effect. Most books define it as the point at which the frequency response has an attenuation of minus 3 dB. In other books, I have seen that they use minus 3 dB per order of the filter, so a second order filter will be minus 6 dB. In this example, we can see that at 1 radian per second, we have an attenuation of minus 3 dB. Now let's talk about the bandwidth and quality factor of a filter. To make things easier, let's take the RLC circuit that we studied in a previous lesson. If we plot the frequency response, we can see that it looks like a bandpass filter. Both the low and high frequencies are being attenuated. If you remember the parameters, we had the term omega 0, which was the natural frequency of the system, and the other parameter was zeta, which defined the damping ratio of the system. Let's play a bit with parameters to see how the system behaves. Moving omega 0 moves the central frequency of the bandpass filter, while moving the damping ratio changes the shape of the frequency response. A high damping ratio creates a large flat zone, but if we lower it, a peak starts showing. A damping of less than 1 made the system oscillate. If we zoom on the peak, we can see that there are 2 points at which the frequency response crosses the minus 3 dB level marked in orange. Based on those 2 points, we can define the parameter called bandwidth. For example, if we set the damping to 0.73, the line crosses minus 3 dB approximately at 0.5 radians and at 2 radians per second. That will give us a bandwidth of 1.5 radians per second. The quality of the filter is defined as the ratio of the cutoff frequency and the bandwidth. If we have the damping ratio, the quality is defined as the reciprocal of 2 times zeta. There is a relation between the damping ratio and the quality of a filter. If the Q of a filter is larger than 0.5, then the filter will oscillate, just like we saw in the lesson of the RLC circuit. Now that we know the characteristics of a filter, let's see how they are built using op-amps. One of the basic building blocks to create a filter is the Sallen key topology. This topology allows to create second-order filters in multiple configurations. In the diagram you can see the circuit. Each of the elements is defined as an impedance, and it could be a resistor or a capacitor. Let's analyze it symbolically so we can obtain a general formula that we can use and we don't have to repeat the analysis later. If you look at the diagram of the Sallen key circuit, it is built using a voltage follower. Assuming that the output voltage of the op-amp is the same as the voltage in the input of the buffer, we can simplify the circuit into two nodes, the node Vx and the node Vout. Let's use nodal analysis to write the equations. First, for the node Vx, we have the current through the impedance Z1, which is the input voltage minus Vx over Z1. The current through Z3 flows out of the node, and it is Vx minus Vout over Z3. Similarly, for Z2, we have Vx minus Vout over Z2. For the node Vout, which is the non-inverting terminal of the op-amp, we have Z2 entering the node, that's Vx minus Vout over Z2. The current through Z4 exits the node, and it is equal to Vout over Z4. We have a system of two equations and two variables. We can easily solve this system using the function solved from the Wolfram language. In the results, we can see the voltage for Vout. We are not interested on Vx. If we write Vout as a transfer function, we obtain the following formula. Let's see the way we use it. This is the low-pass version of the Sallen key architecture. As you can see, some of the impedances are turned into resistors and others into capacitors. Here we can see the replacements. Z1 is now R1, Z2 is R2, Z3 is replaced by the Laplace transform version of the capacitor, just as we saw in the frequency analysis lesson. Similarly, Z4 is replaced by capacitor 2. After simplifying the transfer function, we get the following result. Now the transfer function is in terms of x, which is a complex variable used for frequency analysis. Now let's see how we can obtain the values of the components for the Sallen key filter so we can create an actual low-pass filter that follows a given specification. First, we can see the transfer function we obtained in the last slide. Below, we have the transfer function of a second-order filter with unity gain. As I mentioned before, the second-order systems have been widely studied. That transfer function is how a generic low-pass filter is represented. As next step, we will try to match the terms of the Sallen key filter with the generic low-pass filter. To do that, I have rearranged the transfer function, so the terms s squared in the denominator has a factor of 1. If you look carefully in the numerator, we have omega 0 squared. On the Sallen key transfer function, we have the following term. Omega 0 squared shows up again in the denominator, and in this case, we have the same term in the Sallen key transfer function. We also have the term 2 times zeta omega 0. On the Sallen key transfer function, we have this other term. If we want to convert one transfer function into the other, we have to match each of the terms. The correspondence will be that omega 0 squared has to be equal to 1 over C1 C2 R1 R2. 2 times zeta omega 0 must be equal to this term. If we solve for omega and zeta, we obtain the following formulas. If we would like to design a filter that has a certain specification of omega 0 and quality, we need to find the component values that satisfy these equations. Let's make a numeric example. Let's design a low-pass filter using the Sallen key topology that has a cutoff frequency of 10 kHz and a quality of 0.5, so it will not oscillate. By putting the numeric values into the equations we obtain, we end up with a system of 2 equations and 4 unknowns. In order to simplify the problem, we will pick resistor values of 1 ohm. With that, we can numerically solve the equations and obtain the following capacitor values. Let's create a Bode plot to verify the result. Here we can see that the cutoff is around 62 kiloradians per second, which should be around 10 kHz. However, those values of resistors are not practical. They are too small. If we try larger resistors, for example 100 ohms, we can see that the capacitors become 100 times smaller. In this architecture, we can scale the component values without affecting the characteristics of the filter. If we make the resistor larger, we have to make the capacitors smaller in the same proportion. For example, here I made the resistors 15 kilo ohms. if we divide the capacitors by 15,000, the filter will preserve the same characteristics. Now let's look at the Sallen key high-pass filter. The high-pass version swaps the location of the capacitor and resistor. Here you can see the replacements that are necessary. And below you can see the resulting transfer function. If we want to design a high-pass filter, we could follow the same procedure we follow with the low-pass filter, but I will show you instead a simplified method that will allow us to design the filters in a simpler way. The process of designing an analog filter consists of obtaining a transfer function that has the characteristics we want, then selecting an architecture and try to match the transfer function with the transfer function of the circuit to get the component values. Getting the transfer function is usually the complex part. Fortunately, there exist multiple methods to generate transfer functions of filters. One of them was created by Stephen Butterworth. His method generates filters with no oscillations. Here you can see the code. You don't need to understand it to be able of using it. Let's generate a few filters to see the results. We need to provide the cutoff frequency in radians per second. Then we need to define the order of the filter. For example, a filter of second order with a cutoff frequency of 1 radian per second corresponds to the following transfer function. We can plot the transfer function to see how the Butterworth filter behaves. If we increase the order, the transfer function has more terms in the denominator, and each term corresponds to a Sallen key filter stage that we need to implement. The higher the order, the steeper that the slope will be, making the filter better. Let's see the steps to design a Butterworth filter using Sallen key stages. We can outline the procedure in 4 steps. The first one is to design a normalized low-pass filter. Normalized means that it has a cutoff of 1 radian per second. Then we can convert the low-pass filter into a high-pass filter if that's what we want. Third step is to change the cutoff frequency to the frequency we want to have in the filter. Last, we scale the component values so we have more reasonable values. Let's make a design example showing all these steps. We will start making the normalized Butterworth filter of order 2. This results in the transfer function we explored before. Now we need to match the Sallen key transfer function to the generated Butterworth filter. We can see that matching the terms is quite easy. These are the equations that we need to satisfy to get the normalized filter. If we make resistors R1 and R2 equal to 1 ohm, the equations simplify and we only need to solve for the values of the capacitors. Using the function solve, we can obtain the values of the capacitors, and we obtain C1 equals to the square root of 2 and C2 equals to the reciprocal of the square root of 2. The interesting thing of this method we are following is that we do not need to repeat this step for any other filter design. We can simply take these formulas for any Butterworth filter of order 2. The next step will be converting the normalized low-pass filter to high-pass. In this example, we will convert the filter so we can see the result. If you need a low-pass, you can skip this step. Doing this is very easy. We simply need to perform the following value replacements. The resistance R1 for the high pass will take the value from capacitor C1. Resistor 2 takes the value from the capacitor C2. The capacitors take the value from the resistors. These are the new component values for the high pass filter. We can plot the transfer function of the high pass filter with the new values and corroborate that it is now a high pass filter with a cutoff frequency of 1 radian per second. Next, we need to do the frequency scaling. In this step, we move the cutoff from 1 radian per second to whatever value we want. To do so, we have to replace the values of the capacitors according to the following formulas, which is dividing the value by the frequency we want in radians. In this example, we will move the cutoff frequency to 10 kHz. This results in the following values for the resistors and capacitors. We can plot the transfer function and check that effectively the cutoff has been moved to 10 kHz. Still, the values of the resistors are not very convenient. In the next step, we will scale them in order to get better values. To scale the values, we need to use the following formulas. The resistor can be multiplied by an arbitrary value k, and at the same time, the capacitors are divided by k. In this example, I would like to use capacitors of 1 nanofarad. That requires a value of k equals to 50,915.5. This results in the following scale values. The resistor R1 is approximately 11 kiloohms. The resistor R2 is approximately 20 kiloohms, and both capacitors are 1 nanofarad. By plotting the transfer function, we can see that after scaling, the filter still behaves correctly. These are all the steps to create a Butterworth filter. Complex transfer functions can be created by using multiple Sallen key stages. In the literature, we can find tables containing the initial values for the normalized filters for different orders. Once we have the normalized filter values, we can follow the same steps to adjust the component values of the Sallen key stage. The Butterworth method is not the only one available to create transfer functions of filters. Wolfram Language provides the following alternative methods to generate other filters. In addition to Butterworth, we have Chebyshev 1, Chebyshev 2, and Bessel. We can summarize the methods as follows. Butterworth provides filters that have a flat response at the expense of steepness. The Chebyshev methods provide high steepness at the expense of ripples in the amplitude. In the plot we can see the ripples for a second-order filter and the steepness of the filter. The Bessel method provides minimal phase shifts at the expense of flatness. If we compare the Bessel filter against the Butterworth filter, we can see how the knee of the Butterworth filter is sharper, but the phase transition of the Bessel is smoother. Using these functions to generate a filter is very easy. For example, here we are generating a normalized Butterworth filter of order 2. The resulting transfer function is factorized and it does not look like the one we used. But using the function transfer function expand and chop, we can obtain the transfer function in the form we use in the example. Similarly, we can obtain other filters like Bessel or Chebyshev. One thing we have not covered yet is how to implement odd order filters. For example, the Butterworth of third order has the following transfer function. This transfer function can be split into parts, as an order 1 filter followed by a second order filter. To implement it, we can use the following circuit, which is a Sallen key, but at the input it has connected a simple RC filter. The Sallen key is not the only building block that we can use for creating filters. However, it is the simpler one and it has a reduced number of components. We could use other architectures, for example, the state variable filter. In the diagram you can see the components. It may look complicated, but in reality it is very simple if we split it into blocks. It consists of two similar integrators and a subtractor. The cutoff of the filter is adjusted by changing the gain of these two integrators. One interesting aspect regarding this architecture is that it provides three filter types at the same time: a low pass output, a band pass output, and a high pass. We are not going to analyze the state variable filter in detail during this course, but you can find in the literature the design equations. As a summary for this lesson, we learned the different types of filters and the characteristics that describe them. We learned the Sallen key topology, which is a simple second-order filter. We learned a method to design filters starting from a transfer function like the generated by the Butterworth method. And last, we learned how to implement the transfer functions using Sallen key stages.